Our lesson for today will be looking at chemistry 1502. The topic for today is resonance structures. We'll be looking at lesson 102. Let us start. In lesson 101 of resonance structures, we've looked at the basics of resonance structures, and there's also lesson 103 whereby we continue with this concept. So in this lesson video, we'll be explaining a few concepts which are very important within this topic of resonance structures. The first thing that you should know is the manner on which we present the resonance structures. In lesson 101, you've learned that we can draw different types of Lewis dot diagram of a compound and also be able to tell which one is more stable compared to the other ones. And a compound can have more than two structures, and then we call those structures resonance structures. Now in this lesson, before we start with the examples, you have to understand a few things. You should know that we have different types of errors in chemistry. The first error that you might encounter or you've seen already, the first one is just a simple error that shows a chemical reaction, whereby on the left hand side we refer them to reactants, on the right hand side we refer them to products. So we have reactants reacting to form products on the right hand side. The second error that you might encounter is an error like this. This simply means that particular reaction can be reversible, meaning that if we have, for example, we have A reacting with B to form C and D as our products, we can react C and D to form A and B. So the reaction is basically reversible. So this is another type of errors that you should know. And then we have this arrow here. This arrow simply means the resonance structure. It means that if we have the first structure here, and then you put this type of an arrow to show that A and B are resonance structures, and you can put another one here if you have a third structure. The third arrow that you should know is this arrow. You can see that there's a difference between arrow number 4 and arrow number 5. This simply means that there's a movement, there's a pushing of only one electron, only a movement of one electron. Then you can see that this one is double-headed. Then this simply means that we have two electrons. And then you will see you'll see this arrow when dealing with resonance structures. This is one of the things that you should know. We call this a pushing two electron arrow. Our first example, and by the way, I'll be answering the questions that I provided during the discussion. So we can say this is an explained memorandum or an explained solution manual. So let us start by drawing the resonance structures for this particular compound. Now we have two nitrogens. Then we can clearly see that nitrogens will be our central atoms, and according to Lewis dot diagram 5.2 lesson video, we said that if we have nitrogen bonding 3 times, it doesn't matter whether it's double bond and a single bond, or single bond 3 times, or triple bond, we know that you're going to have lone pairs. So this is one of the basics we should keep in mind when drawing this Lewis dot diagram. So in this case, we can just form a single bond between nitrogen and nitrogen. This will be the first nitrogen, this will be the second nitrogen. And then from there, we can see that we have 4 atoms of oxygen. So we can start by aligning our oxygens like this. Now, doing it like this, forming single bonds, we can put our oxygens here. Now we know for sure that when we have oxygen bonding only 2 times, that is when it is most stable. It will have 2 lone pairs without any charge. If you can calculate the formal charge, you will see that this will yield a 0 formal charge. And then we said if we have oxygen bonding only once, we are going to have something like this. If we calculate the formal charge, you'll find that it will be negative. So in this case, we can see that if we draw it like this, we are going to have the formal charge of each and every nitrogen as 0, but for oxygen we are going to have 4 negative ones. And then if we can add these formal charges, it will definitely not give us 0, because you can see this is it's actually not a polyatomic ion. So we have to draw a formal charge. Actually, we have to draw a Lewis diagram that will not have any ion. And in this case, if we draw it like this, we are going to have -4. So we have to do something with this structure. In chemistry 1501, we've only learned how to draw structures using, actually we never dwelled much in this chapter of resonance structures. So understanding the resonance structures, it will make us be able to draw most complicated Lewis dot diagram. Now in this case, what we can do, how about we form a double bond and a double bond here. Forming double bonds on these oxygens, we know that this oxygen and this one, they will actually be stable. Their formal charges will be 0. And then for this one and this one, we are going to have negative and negative. The sum of the two, it will give us -2. Then since nitrogen, it is not in this nature, it is not stable. If you calculate the formal charge of it, you will find out that it will have 1 and 1. It's actually positive. Like we said in 5.2 Lewis diagram, if nitrogen bonds 4 times, it will yield a positive charge. So in this case, if you have a positive and a positive plus negative and negative, we will definitely have an overall charge of 0. So that is what we actually want. So with this information, we can draw our Lewis diagram correctly. We can just complete this. We are going to have these lone pairs and also here lone pairs, then negative and negative. Let us actually write it here. And then since our oxygen, actually let me fill in this, the formal charges will be 0, and then for each nitrogen we are going to have positive and positive. So this is the first Lewis dot diagram for this particular compound. From here we can go ahead and draw resonant structures. To draw resonance structures, we are going to use this double-headed arrow. And from the original or the first structure, let me not say the original, the first structure, we are going to show how electrons are moving. Let us start by the movement of electrons at this section. So we can see that we have this oxygen with 6 lone pairs. Now we are going to take this pair of electrons, we are going to bring them here. Remember that according to the rules of resonance structures, which we covered in lesson 101, we're also going to emphasize them in the next lesson video, is that when forming resonance structures, we do not tamper with electrons which are bonding with 2 elements, or we refer them to sigma bonds. The sigma bonds are the single bond. Like for example, this, we cannot tamper with this electrons. We cannot tamper with these electrons. We also cannot tamper with these electrons, meaning that we cannot move electrons from this bond to this. Doesn't happen, because you can see that the bond will actually break between the two. And also here, we cannot move the electrons this direction, will break. And then for this one, we cannot move it either way. So from here, like I said, we are going to take this pair of electrons, we bring them here to form a double bond here. Let me actually use a different color. So we have these electrons, we bring them here. And then at the same time, we are going to take these electrons. Remember that a single bond consists of 2 electrons. We're going to take these electrons and we are going to bring them here. And the rules, one of the rules that you should understand, we cannot have these arrows pointing the same, different direction. You cannot have them pointing this direction, or when it points this direction and then we have another arrow pointing this direction. No, they must be in the same direction. So in this case, we are going to have these electrons moving this direction. Then on the next structure, that is when we represent the new change. We have our nitrogens here, 1 and 2, and then we no longer have a single bond here. Remember that we no longer have electrons here, they've shifted, so they formed this single bond here. Then this single bond will join this existing single bond to form double bond. We also refer them to pi bonds. Then representing this section here, we had double bond, but we no longer have double bond because those electrons, they've shifted to this oxygen. So it means that instead of 2 lone pairs, we have 3. Then the 16 electrons that are here. And then the rest of the structure we can just redraw the way it is. Actually, we had a double bond here. Then we have oxygen here. So the formal charge of this one is negative. This one, it was, you can see it was positive here. It was actually 0, and then now it has a negative charge. And then since nitrogen still has the 4 bonds, it will have positive charge. So this is one of the resonance structure for N2O4. Now from this one, we can form another resonance structure. Or let us take it from the original one. We can produce another resonance structure. Instead of pushing these arrows, pushing these electrons here, we can push these ones here. And then at the same time, we push these ones here. So you can see the reason why we have to push these electrons like this, in this manner. Remember that we are trying to maintain these bonds for nitrogen so that this charge does not change. So in order for it to yield a positive charge, we really need 4 bonds. So if you can only push this one here and then try to tamper with anything here without making any changes within this region, clearly shows that nitrogen will have only 3 bonds, and then it will be neutral, then remember that we are trying to maintain that zero charge for the overall compound. So the resonance structure, we are going to have something like this. So if you push this double bond here, we are going to have lone pairs. I mean, those electrons, they've shifted from the double bond to oxygen, it will yield a negative charge. At the same time, these electrons here will come here, meaning that we no longer have a single bond but a double bond. So in this case, we still have our nitrogens as positive. If we can calculate the overall, we are going to have total charge of 0. Now we do have the last resonance structure that we can present for this particular example. The last resonance structure, I'll just write it down. You can go ahead and pause the video, play the video to verify it. You're going to have something like this. The procedure is still the same. It will be like this. Now in this case, which one is the most stable? If you can check the formal charges, they result into 0, all of them. And if you can check, we say the most stable one is the one that contains more formal charges which are close to 0. In this case, the formal charges are the same. They are just rotating within the oxygen atoms. So in this case, we don't have any stable or not or unstable structure. They're all the same. For this example, this is how we draw resonance structures. There is lesson 103 of resonance structure, whereby we'll be looking at the major and the minor contributors. And we also check which one is more stable based on electronegativity. So just make sure you watch the lesson video, and then you'll understand the resonance structures in detail.